In this video, I will show you how to evaluate definite integrals using inverse trig functions. Here are the three inverse trig integral rules that you have to memorize. I will show you how to use them, but pause your screen and memorize them now. Okay, number 24. Which one of these three rules do you think we are using this time? I'm thinking this one. I see that we have this little x out in the front, just like the u. I see that we have the square root, we have the variable, and then minus the constant, variable minus the constant. It's all matching up with the third one. So arcsecant it is. To make it match more perfectly, I'm going to take this exponent of 2 outside of some parentheses, so I have the quantity of 2x that is now being squared. That will be the same thing as 4x squared, because if I square the 2 and I square the x, I will get 4x squared. Now that lets me know that the u must be 2x. So let's get that going. So u is equal to 2x. That means that u prime must be 2. Also, a must be 3, because that's the square root of 9. I've made the u substitution, so 2x is now a u, but we will replace dx with du divided by u prime, which is 2. I forgot to mention that I intentionally dropped the limits of integration because I knew I was going to do u substitution. And these are x values. The original limits of integration are x values. So you cannot mix x's and u's. So one way to handle it is just to take the limits off, treat it as an indefinite integral until the end of the problem. And then we will bring the limits back at the end. Speaking of not wanting to mix u and x, we're going to have to do something about the fact that we have this x right here. Well, let's see. We know that u is equal to 2x. That means x is going to equal 1/2 u if we just divide both sides by 2. So let's replace x with 1/2 u. This works out very nicely because now the 2 that we have in the denominator cancels out the 1/2 when these multiply together to make 1. Now we have this perfect match with the rule. So let's go ahead and rewrite this with arcsecant. We have 1 over a. Remember that a is 3. So I write 1 over 3. Arcsecant. This is the one with the absolute value. So we write the absolute value of u over a. So that's u over 3 plus c. All we have to do is let u equal 2x again. And let's bring back the limits of integration. Putting 2x back in for u, we have this. And here's how you get the limits of integration back in. I'm going to put this in parentheses, and I'm going to put a vertical line next to it. And here's where you write the limits of integration. Radical 3 to 3. This means that we find the value at the upper limit minus the value at the lower limit. So here is the value at the upper limit. I just substituted 3 for x, and here's the minus. Now here comes the value at the lower limit. Now, am I allowed to put a box around this and put this as my final answer on a free response question? No. Even though we don't need to simplify, we do have to evaluate trig functions, and that's what we have happening here. So you can't stop here. So let's keep going. Notice that we have 3 over 3. So these will certainly cancel each other out. So from that, we have 1/3 arcsecant of 2. Also, we no longer need the absolute value. This is a positive number, so the absolute value makes no difference. Minus 1/3 arcsecant. So what am I going to do with this? I want you to focus on this part of it, radical 3 over 3. I think it's worth memorizing that radical 3 over 3 is the same as 1 over radical 3. It's just that this form has the denominator rationalized, but these are the same. I actually want to turn this back into 1 over radical 3 instead of radical 3 over 3, and I'll show you why in a second. But we do have this 2 in front, so this is really 2 times radical 3 over 3. So that makes this 2 times 1 over radical 3. And you can probably see that that is going to be the same as 2 over radical 3. So 2 radical 3 over 3 is the same as 2 over radical 3. So let's make that change and have the arcsecant of 2 over radical 3. Now, here's why I went out of my way to write it this way. I am more comfortable with arc cosine than I am with arc secant. So I know that cosine is the reciprocal of secant, so this would have the same value if I replace this with arc cosine and do the reciprocal here. So this arc secant of 2 has the same value as the arc cosine of 1/2. And then I still have my minus 1/3. And instead of arc secant 2 over radical 3, this would be the same as arc cosine radical 3 over 2. So that's why I wrote it this way, because when we do the reciprocal, we get this nice radical 3 over 2, and we have memorized what the cosine of various angles that will equal radical 3 over 2. This is a part of our memorized set of facts. When you evaluate an inverse trig function, you sort of think about it this way. The arc cosine of 1/2 is the answer to the question, cosine of what angle is equal to 1/2? We know that the cosine of pi over 3 is equal to 1/2, so this has a value of pi over 3. To evaluate this one, ask yourself, the cosine of what angle is equal to radical 3 over 2? We have memorized that the cosine of pi over 6 is radical 3 over 2, so the answer, the value of this inverse cosine is pi over 6. I should mention that inverse trig functions have restrictions. For example, the inverse cosine that we were just working with is only allowed to be between 0 and pi. But the two values that we found, which were pi over 3 and pi over 6, they are both in the first quadrant, so that was fine. So we actually could put a box around this and call it the final answer for a free response question. I am going to keep going a little bit further because I want to show you what it would look like for a multiple choice question. If I multiply the 3 times the 3, I have pi over 9. So now I have pi over 9 minus pi over 18. Let's go ahead and make like denominators by multiplying by 2 over 2. So this is now 2 pi over 18 minus pi over 18, which will be pi over 18. And this is the final answer. And this is likely what you would see as an option for a multiple choice question. Which one of the 3 inverse trig integral rules do you think we will use on this problem? I'm betting on the middle one, arcsine. I see the square root, so that leaves out arctangent. And I notice that we have the constant minus the variable. And in the arcsine, we have the constant minus the variable. Plus, there's nothing in front of the radical, and for arcsecant, there's usually something in front of the radical. So it's looking like arcsine. In the rule, we have this u squared happening right here. So to make this look more like the rule, I want to take e to the negative 2x and somehow write it as something squared. So how about if I put in some parentheses and I want to pull out this 2. I can do that. That will leave behind e to the negative x power. When you raise a power to a power, you multiply. So if I wanted to simplify this again, I would multiply 2 times negative x. That would make negative 2x. That means that these are equivalent. But this brings me one step closer because now I have u squared, which tells me what u is. So apparently u is e to the negative x power. That means that u prime is going to equal, let's see, the derivative of e to the something is still e to the something. However, chain rule, you have to multiply by the derivative of the inner function. In this case, that's negative 1. I'm going to put this negative in the front though. I also need to know what a is. A squared is right here. I see the 1 right here. 1 squared is 1. So that means a is 1. A is always the square root of what you see right here. So a is 1. Let's go ahead and do the substitution and see what happens. Oh, by the way, notice that I'm intentionally leaving off the limits of integration for now. That's because I'm doing u substitution, and so I'm switching from these x values to values of u. So I find the easiest thing to do is usually just to leave off the limits of integration completely until the end when we bring the x's back. If you leave the limits of integration on during the problem, even while you're doing the u substitution, you will lose a point on the AP exam. Now I could switch these over to u's. I could say, hey, u is equal to e to the negative natural log 4. I could plug these limits into this formula for u and turn them into values of u. That's fine. Then you can keep them. But unless you feel like doing that, just leave them off, and that's what I'm going to do right now. Anyway, I have e to the negative x power, and then I have the square root of 1 minus u squared. Instead of dx, I will write du over u prime, which is negative e to the negative x power. So negative e to the negative x power. Right away, I notice that we have e to the negative x in the numerator and the denominator. Those will cancel each other out. However, there's still a negative sign, so don't forget about that. Now that we have a perfect match with the rule, we can go ahead and integrate. So we have arcsine u over a. So I'm going to write down arcsine u over a. Well, a is 1, so I'm just going to write arcsine u plus c. Don't forget the negative sign in the very front. I am going to bring that down. Now let's go ahead and substitute e to the negative x power back in for u. So I will have negative arcsine. You know what? Instead of putting e to the negative x power, I'm sure you won't mind if I go ahead and put 1 over e to the x power. Now instead of putting plus c, I'm going to go ahead and bring back my limits of integration. This is a definite integral, so let's not forget about that. Put a vertical line and show your limits of integration. So natural log 2 to natural log 4. This reminds me that I need to find the value at 4 and then subtract the value at 2. When I say I need the value at natural log 4, it means I substitute natural log 4 for x. So this is the value at natural log 4, and you see the minus, and this is the value at natural log 2. Clearly, minus a negative is addition, so I'm just going to go ahead and put a plus right here. So natural log and base e are inverse functions. So those are going to cancel each other out. So the base e and the natural log cancel each other out. So this is just going to be a 4, so 1/4. Similarly, the base e and natural log right here cancel each other out. That's just going to be a 2, so 1/2. One of these terms we can evaluate further, so we need to keep going. And it is this one that we can evaluate further. When you evaluate an inverse trig function, you ask yourself something like this. The sine of what angle is equal to 1/2? And this is a question that we can answer without a calculator. The sine of pi over 6 is 1/2. So the value of this arcsine expression is pi over 6. That's as far as we can go without a calculator. So this is the final answer. Which rule do you think we will use for problem number 32? I am betting on the middle rule, arcsine. I see that we have the square root. That pretty much rules out arctangent. And then I see that we have the constant minus the variable squared. And that's what we have here, the constant minus the variable squared. Actually, I changed my mind. This rule will not work. In fact, none of these three rules will work. The denominator already matches perfectly, so there is no u substitution for me to do here. And so therefore, there's nothing to cancel out the arc cosine, which is in my way. So we need a completely different strategy. Here is the memorized rule from first semester that will help us solve this problem. Remember that the derivative of arcsine is 1 over the square root of 1 minus x squared. So the derivative of arc cosine is just negative 1 over the square root of 1 minus x squared. I'm mentioning that because you see the arc cosine in the numerator. So what if we let u equal arc cosine x? Think about what u prime would be. U prime would be this, negative 1 over the square root of 1 minus x squared. When you see the derivative elsewhere in the problem, there's a good chance that you are on the right track with your u substitution. So let's go ahead and do the u substitution. As we do so, remove the limits of integration. We will put them back in again when we switch everything back to x's. So in the numerator, we simply have u. So for right now, I have u over the square root of 1 minus x squared. Instead of dx, I will write du over u prime. But u prime is this, negative 1 over the square root of 1 minus x squared. Notice that we have a square root of 1 minus x squared in the numerator and the square root of 1 minus x squared in the denominator. So when we multiply these straight across, these will cancel each other out. That's just going to leave negative 1, which we can put in the front. So I will have a negative 1, and then the integral of u du. Using the power rule of integration, I will increase the power by 1. So I get u squared, and then I divide by the new power. So that's going to be 1/2 in the front, except it will be negative 1/2 because of the negative sign that I already have, plus c. Substituting arc cosine x back in for u, we have this. Instead of putting the plus c, I am going to put the limits of integration back in. Don't forget, this is a definite integral. So I'm going to put 0 to 1 over radical 2 right here. So this tells me that I need to find the value at 1 over radical 2 and subtract the value at 0. So here's the value at 1 over radical 2 minus the value at 0. Minus a negative is a positive, so I will go ahead and replace these two minuses with a plus. When you try to evaluate an inverse trig function like this, you ask yourself a question like, the cosine of what angle is equal to 1 over radical 2? Hopefully you know that the answer here is pi over 4. So that's the value of arc cosine 1 over radical 2. Looking at the arc cosine of 0, you ask yourself the question, the cosine of what angle is equal to 0? You might find yourself thinking of two answers, pi over 2 or negative pi over 2, or maybe 3 pi over 2. However, if we look back at the restrictions on these inverse trig functions, we remember that inverse cosine or arc cosine is only defined between 0 and pi. So we cannot pick negative pi over 2 or 3 pi over 2. We can only go with positive pi over 2. So that brings us to this. Pi over 4 squared is pi squared over 16. So I have negative 1/2 times pi squared over 16 plus 1/2 times pi squared over 4. Well, this is going to be negative pi squared over 32. 2 times 16 is 32. Plus pi squared over 8. It would be nice to have like denominators. So what if we multiplied by 4 over 4? So now we have negative pi squared over 32 plus 4 pi squared over 32. That will make 3 pi squared over 32. And this is the final answer.